Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to just imagine something for a second.
Okay.
Picture a ghost, but, not a sheet-wearing, hovering in a hallway kind of ghost.
Right, something a bit more substantial.
Exactly. I'm talking about a cosmic ghost, an entity that possesses the mass of 1 million of our suns.
That is a lot of math.
It really is.
Yeah.
And it's just wandering entirely invisible through the dark, quiet suburbs of a distant galaxy.
Just completely out in the open, but totally hidden.
Yeah, because it emits absolutely zero light. I mean, it makes no sound. It is a perfect void drifting through the blackness of space.
It is the ultimate cosmic ambush, really.
Right. And the only reason we even know this staggering thing is out there, the only reason we can perceive it at all, is because it just violently ate a star.
1 million solar masses of pure gravity, completely hidden until the exact moment a star takes one wrong step.
And today is July 27, 2026, and the entire world of astronomy just realized they were looking at a massive reality-bending paradigm shift.
Because it completely breaks the rules we thought we knew.
It totally does. Because we are looking at the discovery of one of the universe's absolute rarest events. I'm talking about a supermassive black hole, a true monster that is not where it is supposed to be.
It's tens of thousands of light years away from its designated home.
Right. It is a rogue, a wanderer. But, before we get to the fact that this black hole is wandering through the galactic suburbs, we really need to set the scene.
Yeah, we have to talk about the catalyst.
Exactly. The murder scene itself. What exactly happens physically when a star wanders too close to an invisible monster?
Well, the actual scientific term for this catalyst is a tidal disruption event. Or we usually just call it a TDE.
A TDE. Got it.
And it is truly one of the most violent physical processes in the known universe. To understand what happens, you really have to look at the mechanics of gravity.
Okay.
Specifically, you have to understand that the gravity of a supermassive black hole isn't just strong. It creates this extreme gradient.
A gradient, meaning the pull is significantly stronger the closer you get.
Right, exactly.
But wait, gravity always gets stronger the closer you get to something? That's just how gravity works. Why is it so extreme here that it literally shreds a star?
So it has to do with the density and the extreme proximity. Imagine a star, very similar to our own sun, just tracing a path through a galaxy.
Okay, tracing its path.
Over millions of years, its orbit happens to drift a little too close to this hidden million solar mass black hole.
Just a little too close.
Right. And because a black hole is so incredibly dense, the star can get extremely close to the center of that mass without hitting a physical surface.
Because it's a singularity, not a giant rock.
Yes. So as it approaches, the gravitational pull on the side of the star facing the black hole becomes exponentially stronger than the pull on the far side of the star.
Oh, well. Okay, so if the star is, say, 1 million miles wide, the front edge of the star is 1 million miles deeper into the black hole's gravity well than the back edge.
Precisely. And that difference in gravitational pull across the diameter of the star, that is what we call the tidal force.
Like the tides on Earth, but cranked up to 1 trillion.
Exactly like that. And eventually, that tidal force exceeds the star's own internal gravity.
The force that's holding the star together is a burning sphere of plasma.
Yeah, that force is simply overwhelmed by the difference in the black hole's pull.
So the star doesn't just bump into it like a car crash.
No, not at all.
The front is yanked so much harder than the back that the star simply cannot hold itself together. It fails structurally.
It is literally torn apart. The term astrophysicists sometimes use is spaghettification.
Spaghettification? That sounds a bit whimsical for an absolute cataclysm.
I know, it really does, but it's accurate. The star is stretched into a long, thin stream of superheated stellar material.
Like a noodle.
Like a noodle of plasma, yeah. But what happens next is what makes this detectable to us here on Earth.
Because it doesn't just quietly fall straight down into the void.
No, it definitely doesn't. The crumbs of the splintering star, this immense volume of gas and plasma, they get caught in the black hole's gravitational grip.
And they start to orbit.
They do. They begin to swirl around the black hole, forming what we call an accretion disk.
Okay, so it's like water circling a drain.
Very similar, yes.
But the drain is a bottomless pit in space-time. And the water is superheated plasma moving at, what, a fraction of the speed of light.
A significant fraction of the speed of light. And that speed is the key to everything.
Why is the speed so important?
Because the material is orbiting so incredibly fast, the friction within the gas is unimaginable.
Friction in space.
Yeah, as the layers of plasma rub against each other in that swirling disk, they undergo intense compression and friction.
Which generates heat.
It heats the material to temperatures that defy human comprehension. We're talking millions of degrees.
Millions of degrees. That is insane.
It is. And this heat creates an incredibly brilliant glow, radiating intense ultraviolet light and X-rays across the cosmos.
It's basically screaming its existence out into the universe.
Exactly. And furthermore, the immense magnetic fields and the rotational energy involved in this whole process can cause the black hole to launch a relativistic jet into space.
A relativistic jet. What is that?
It's basically a highly concentrated beam of energy and matter shooting outward along the poles of the black hole, moving at nearly the speed of light.
So it's like a cosmic lighthouse beam.
Yeah.
It's the universe's most dramatic dinner bell.
That's a great way to put it.
Because black holes themselves emit zero light. I mean, you could be looking right at one and see nothing but the darkness of space.
Right. They are functionally invisible.
But this TDE, this destruction of the star, completely lights up the dark.
Assistant Professor Igor Andrioni down at UNC Chapel Hill perfectly described these events. He called them cosmic billboards.
Cosmic billboards. I like that.
Yeah, because they are quite literally advertising the presence of something that would otherwise remain completely stubbornly invisible.
Which is huge for astronomy.
It's a scientific goldmine. Catching these events in the act illuminates the actual mechanics of how massive black holes feed.
Okay, but if we are just sitting around waiting for a star to accidentally bump into an invisible black hole, how often does that actually happen?
Well, space is famously very empty.
Right. So it can't be that often.
It is extraordinarily rare. On average, a tidal disruption event happens only once every 100,000 years anywhere in a given galaxy.
Wait. Once every 100,000 years for a whole galaxy.
That is the average rate, yes.
But a galaxy has billions of stars. You're telling me out of billions of stars circling around, this crash only happens once every 100 millennia?
It is a true testament to exactly what you just said. Space is incredibly empty. The distances between stars are vast.
Unimaginably vast.
And the distances between a star and a central black hole are even vaster. The orbital alignment required for a star to perfectly cross that fatal threshold, what we call the tidal radius, is mathematically highly improbable.
So it can't just be passing through the neighborhood.
No, its specific trajectory has to intersect a very precise, very narrow zone right around the black hole.
Man, to put that 100,000-year timeline in perspective for you listening. 100,000 years ago, anatomically modern humans were just starting to seriously migrate out of Africa.
It's a massive span of time.
Neanderthals were still the dominant hominins in Europe back then. We'd gone from stone tools to quantum computers in the time it takes for a single galaxy to produce one of these flashes.
Which is exactly why, in the past decade of intensive modern astronomy, with all our advanced telescopes constantly scanning the skies, astronomers have only identified a little over 100 of these TDEs in total.
100? Across millions of galaxies?
Across the millions of galaxies we can actively observe, yes.
It makes me think of an analogy.
Let's hear it.
Okay, imagine you are in a massive pitch-black warehouse. You have absolutely no idea what's in the room, but you suspect there's a giant invisible spinning fan blade somewhere in there.
Okay, a dangerous room.
Very. And you can't use a flashlight. You can't make a sound. The only way you can find that fan blade is by taking a glowing, exploding paint bomb and tossing it into the dark.
I see where this is going.
Right. If you toss it and it hits the floor, nothing happens. If you toss it and it hits a wall, nothing happens.
Because it's not hitting the target.
Exactly. But if you just happen to toss that paint bomb perfectly into the spinning blades, boom.
It shreds.
The paint is violently shredded, it heats up, it splatters everywhere, and suddenly, for just a brief few weeks or months, the destruction of the paint reveals the exact shape, location, and violence of the monster in the dark.
That is a highly accurate visualization, actually. The star is your paint bomb.
Right.
The destruction of the star is the only mechanism that renders the invisible fan blade, the black hole, temporarily visible.
But here's the thing. Finding one of these paint bombs, finding a TDE, is not the real paradigm shift here today, is it?
No, it's not.
Because we found 100 of them before.
Yeah.
The universe-breaking mystery here is where this specific paint bomb went off.
Which brings us to the specific event designated as TDE 2025 ABCR.
Catchy name.
They always are in astronomy.
So researchers track this massive flare to a nearby galaxy. It has an even catchier, very poetic catalog name.
Oh, YZJJ014656.04152214.7.
Wow, you memorized that. We'll just call it the WYSA galaxy for short.
What an idea.
Now, usually when we see a TDE, it's dead center in the galaxy, right?
Almost always.
But TDE 2025 ABCR happened 30,000 light years away from the center.
Which represents the farthest offset ever observed for an optically discovered tidal disruption event.
30,000 light years. That's a massive distance.
It is, and it breaks a fundamental rule that astronomers have operated under for a very long time.
Which rule is that?
Well, Jonathan Carney, who's a PhD student in physics and astronomy at UNC Chapel Hill, pointed this out very clearly. He noted that almost every tidal disruption event we have ever observed has occurred at the absolute center of a galaxy.
Because that is where the giant black holes live.
Exactly. The galactic nucleus is where the supermassive black holes reside. It's where the gravitational well of the galaxy is the deepest.
It's like the drain at the bottom of a massive sink.
Right. It's where the most matter has accumulated over billions of years. That is where we expect the biggest monsters to be.
So to find a tidal disruption event tens of thousands of light years away from the center.
It implies there is a massive black hole lurking in a place we would normally never, ever expect to find one.
I have to stop you here, though, because the scale and the physics are kind of messing with my head.
How so?
The black hole responsible for this event is estimated to be roughly 1 million times the mass of our sun. 1 million solar masses.
That is the current estimate, yes.
How on earth do you hide something with 1 million solar masses in the quiet suburbs of a galaxy?
I mean, I feel like its gravity would just be completely tearing the neighborhood apart.
It's a fair assumption to make.
Wouldn't it be like a cosmic vacuum cleaner? Wouldn't we notice all the stars around it swirling down a drain before a TDE even happens? It is a very common misconception about black holes, this idea that they are cosmic vacuum cleaners.
Because pop culture always shows them sucking everything in.
Right. We assume something that massive must be inherently disruptive, just constantly pulling in everything around it. But you really have to remember two things here.
Okay, what are they?
First, the sheer scale of the space we are talking about. And second, the inverse square law of gravity.
Okay, let's break down the inverse square law, because that sounds like the actual key to this whole hiding trick.
It absolutely is. Gravity is entirely dependent on distance. The inverse square law basically states that if you double the distance between two objects, the gravitational force doesn't just drop by half.
It doesn't.
No, it drops by a factor of 4. It weakens exponentially the further away you get.
Oh, wow.
If you triple the distance, the force is 9 times weaker.
So gravity basically falls off a cliff once you take a few steps away from the source.
Precisely. Let me give you a local example. If you were to replace our own sun right now with a black hole of the exact same mass, 1 solar mass, Earth would not get sucked in.
Wait, really? We wouldn't just spiral to our doom?
Not at all. The Earth would continue orbiting in the exact same path in exactly 365 days.
Because the mass hasn't changed.
Because the mass hasn't changed and our distance hasn't changed.
The only difference is that we'd all freeze and it would get very, very dark.
It would be a bad day for life on Earth, yes. But gravitationally, nothing changes.
So let's apply that to this wandering monster in the WYSA galaxy. It has the mass of 1 million suns.
Right. And 1 million solar masses is immense compared to our sun, obviously. But on a galactic scale, it's just a drop in the ocean.
Really? 1 million suns is a drop.
The entire galaxy weighs billions or even trillions of solar masses. 30,000 light years from the center puts this black hole out in the outer galactic disk, or maybe even the halo.
Which is the sparsely populated part of town.
Exactly. These are regions where the density of stars is significantly lower than in the packed galactic core.
So it's not packed like sardines out there. The stars have a lot of elbow room.
Lots of room. So because of that inverse square law we just talked about, unless a star crosses that very specific, very narrow threshold right next to the black hole's event horizon, it will simply orbit the black hole safely.
Or just pass right by it.
Yes, completely unaffected in any catastrophic way.
So it really isn't a vacuum cleaner at all. It's more like, it's like a really, really deep pothole on a very wide, empty, dark highway.
I like that.
Like if you don't drive your tire directly over it, you're totally fine. You don't even know it's there.
That is a perfect way to look at it. And scientists have actually theorized for a while that these wandering black holes likely exist in massive galaxies.
They suspected they were out there.
Oh, definitely. The mathematics and the really complex computer simulations of galactic evolution strongly suggest they should be out there wandering around.
But knowing they exist in a computer model and actually finding one in the dark are two very different things.
Extremely different. As Jonathan Carney highlighted, they are notoriously difficult to study because unless they are actively feeding, unless they briefly disrupt a star like this one did, they produce absolutely no light.
They're perfectly camouflaged against the darkness of empty space.
Literally invisible.
Okay, so if a 1 million solar mass black hole does not naturally belong in the galactic suburbs, if it's supposed to be downtown in the galactic core where it was born, how in the universe did it get 30,000 light years away?
That is the big question.
I mean, what could possibly have the leverage to move an object that weighs 1 million times more than our sun?
Well, astrophysics offers two leading theoretical scenarios for how a supermassive black hole becomes a wanderer, a rogue drifting far from home.
Okay, let's hear them.
Both scenarios are rooted in immense violence and cosmic scale upheaval. The first theory proposes that this black hole is essentially a remnant left behind after a massive galactic merger in the distant past.
Let's talk about a galactic merger for a second. We're talking about two entirely separate galaxies colliding with each other, right?
Yes, a cosmic collision. Picture a massive galaxy and a smaller satellite galaxy nearby. Over billions of years, their mutual gravitational attraction slowly draws them together.
Billions of years.
Yeah.
So this is not a fast crash.
No, it is an incredibly slow, majestic, and entirely destructive process. As the two galaxies merge, their outer halos touch first.
What happens then?
Gas clouds collide, which compresses the gas and ignites massive bursts of new star formation. It would look like fireworks on a cosmic scale.
But do the actual stars crash into each other?
Surprisingly, no. The stars themselves rarely collide because of the vast distances between them, but their orbits are thrown into complete and utter chaos.
Okay, but what happens to the black holes? Because both of these galaxies started with their own supermassive black hole in their respective centers, right?
Most galaxies do, yes. Now, in a perfect symmetrical merger, the two central black holes would undergo a process called dynamical friction.
Dynamical friction.
They would interact with the gas and stars around them, slowly losing orbital energy, and they'd gradually sink to the center of the newly combined larger galaxy.
So they sort of spiral down the new drain together.
Exactly. Eventually, they would orbit each other in a binary pair and, over millions of years, merge into one even larger supermassive black hole.
That sounds very neat and orderly, but I'm guessing space isn't always that tidy.
Far from it. Mergers are very messy, asymmetrical events. Sometimes, the smaller galaxy is essentially stripped apart before it even reaches the center.
Stripped apart how?
Its outer layers of stars and gas are literally peeled away by the tidal forces of the larger galaxy.
So it's just dismantled.
Right. And by the time the smaller galaxy is fully swallowed, its central black hole is left completely stranded.
Because all the stuff around it that was helping it sink is gone.
Yes, it loses its surrounding mass and never manages to sink to the new galactic core through that dynamical friction. It simply gets marooned out in the newly expanded outer halo of the merged galaxy.
Just orbiting aimlessly.
Just wandering.
So it's basically the orphaned heart of a dead, consumed galaxy, just floating through the outer ruins of its former home. That is incredibly poetic and kind of sad.
It is a profound cosmic artifact of a billion-year-old collision.
Okay, what's the second theory? Because you said there were two.
There is a second, perhaps even more violent theory, the ejection scenario.
Ejection.
This theory suggests that the black hole wasn't passively left behind by a merger, but was actively, violently thrown outward from the center of its own galaxy.
Wait. Thrown?
Yes.
How do you throw 1 million suns? What could possibly generate enough force to eject a supermassive black hole?
Gravity itself, specifically the chaotic gravitational interactions between multiple massive black holes near a galaxy center.
Multiple? Like more than two?
Exactly. This often happens in the chaotic aftermath of not just one, but multiple successive galactic mergers. Imagine a scenario where three massive black holes end up drawn toward the center of a newly forming galaxy before they have a chance to merge.
Okay, I can see where this is going. It's like a cosmic game of billiards, but the billiard balls weigh millions of solar masses.
And this brings us to one of the most famously unsolvable concepts in astrophysics, the three-body problem.
Oh, I've heard of this. It's notorious.
It is. In classical mechanics, if you have two massive bodies orbiting each other, like the Earth and the Sun, or two black holes, their orbits are stable, predictable, and mathematically elegant.
Right, it's a balanced equation. We can calculate where the Earth will be next year with perfect accuracy.
We can calculate their positions billions of years into the future. But the moment you introduce a third massive body into that gravitational system, the mathematics completely breaks down.
It just stops working.
The system becomes inherently chaotic and unstable. There is no simple mathematical solution. The three black holes whip around each other faster and faster, exchanging orbital energy in totally unpredictable ways.
Because every time body A gets close to body B, body C is pulling on them from a different angle, constantly changing the trajectories.
Precisely. They are constantly stealing kinetic energy from one another. And in these unstable three-body interactions, the inevitable outcome is almost always an ejection.
Someone gets kicked out of the club.
Always. The laws of conservation of energy and angular momentum basically demand a resolution to the chaos. The lightest of the three objects, or the one that simply hits the wrong angle at the wrong time in this complex dance, receives a massive sudden kick of kinetic energy.
So it gets violently kicked off the billiard table.
It is quite literally slingshotted outward. And this kick is so powerful, it overcomes the immense escape velocity of the entire galactic center.
That is mind-boggling.
Propelled by the very gravitational forces that drew it inward in the first place, it is flung out into the galactic halo, destined to wander the suburbs forever.
I really want you listening to this right now to just pause and sit with the sheer scale of time involved here.
It's hard to wrap your head around.
It really is. Because whether this black hole was stranded by a slow-motion merger or kicked out in a chaotic gravitational slingshot, these are events that happened millions, possibly billions of years ago.
Deep time.
Right. Which means this giant, this entity with the mass of 1 million suns, has just been silently, stealthily drifting through the dark for eons.
For longer than the Earth has had complex life.
Totally undetectable, emitting no light, just waiting. For millions of years it waited until one single unlucky star finally crossed its path and brushed the edge of that pothole.
It highlights the vast, quiet patience of the universe. Timescales that basically render human history irrelevant.
But, a black hole waiting in the dark is only half the equation here.
Right, we still had to find it.
Because for 1 billion years it was invisible. And frankly, if we had been looking, we wouldn't have seen it. Even when the star exploded, we almost missed it.
We came very close to missing it.
Finding this thing required us to actually overcome our own deeply ingrained blind spots. We had to fundamentally change how we look at the night sky. And that brings us to the methodology and kind of the unsung hero of this entire discovery.
The actual mechanism by which we found a single flash of light 30,000 light years away from where it was supposed to be.
Because we didn't just stumble on this by having a guy look through an eyepiece at the exact right second.
No, those days are long gone.
We found this using artificial intelligence, specifically an AI classification tool called datasets.
Yes.
And this tool was originally developed by Robert Stein at the University of Maryland and NASA Goddard.
And its application here is a total masterclass in modern astronomical technique because it addresses a fundamental crisis in the field right now.
A crisis.
Yes. But to understand why the AI is so necessary, we have to look at how Akash Anumarlapudi, who is a postdoctoral researcher in physics and astronomy at UNC Chapel Hill, how he actually utilized it.
Okay, what did he do differently?
He adapted this desk-to-score AI to scan enormous amounts of telescope data. But here is the critical innovation he adapted it specifically to search for TDE candidates away from galaxy centers.
Okay, stop, because this is the part that completely blew my mind when I first learned about this.
It's a great twist.
Are you telling me that because human scientists assumed that massive black holes only lived in the center of galaxies, we literally programmed our own blind spots into our telescopes?
Yes.
Like we were deliberately ignoring the outer edges because we thought we already knew nothing was there.
That is essentially correct, and it is a fascinating look at the intersection of human bias and computational limits.
How does that even happen?
Well, in astronomy, you are dealing with an infinite sky and very limited computational resources. You have to prioritize where you look and how you filter the data.
You can't look at everything all the time.
Exactly. For nearly a century, the established theory, which was backed by almost every observation we had ever made, mind you, dictated that supermassive black holes exist exclusively in galactic nuclei.
So it wasn't a crazy assumption, it was based on past data.
Right. Therefore, when astronomers wrote the initial algorithms to sift through telescope data to find TDEs, they heavily weighted the galactic center.
So they literally wrote code that said, if a flash of light happens far away from the center, ignore it. It's not a TDE.
Functionally, yes. If a flash occurred in the outer suburbs of a galaxy, the algorithms were trained to classify it as a supernova, or maybe a variable star, or perhaps just an observational error.
Because supernovas happen everywhere.
Supernovae happen all over galaxies, yes. But a TDE in the suburbs, it didn't fit the established model, so the system filtered it out as noise or miscategorized it. We trained the machines to ignore the anomalies.
We let our assumptions dictate our reality.
We did.
We told the computers, don't look over there, there's nothing interesting. So we only found this wandering giant because we finally told the AI to remove our human assumptions.
Precisely. Akash Anumarlapudi stated it perfectly. By explicitly removing the constraint that these events only happen in the galactic center, the team was able to find a black hole that would have otherwise been completely missed by standard search parameters.
Just looked at the raw data.
Exactly. The AI, once unchained from that geographical bias, just looked at the physics. It analyzed the characteristics of the flash and flagged it, regardless of the zip code it occurred in.
Wait, how does an AI know the difference between a star exploding as a supernova in the suburbs and a star being shredded by a black hole in the suburbs?
That's the real magic of it.
Because they're both just bright flashes of light in a telescope, right?
Yeah.
To me, a flash is a flash.
That is where the power of modern machine learning really comes in. AI doesn't just see a flash of light, it analyzes the light curve and the spectral signature.
Okay, a light curve.
Yeah.
That means how the brightness changes over time.
Yeah, exactly. When a star explodes as a supernova, it expands outward. It gets very bright very quickly, and then it cools off in a very specific, predictable mathematical curve.
Okay, so it has a known fingerprint.
Yes. Furthermore, the light from a supernova contains the chemical signatures of heavy elements synthesized in the explosion. Things like iron, nickel, silicon.
So what does a TDE look like to an AI then? How is it different?
A TDE looks fundamentally different. Remember the accretion disk we talked about earlier?
The swirling superheated plasma.
Yes. That disk stays incredibly hot for a much longer time than a supernova. It emits massive amounts of ultraviolet light and X-rays, far more than a typical exploding star.
So it's hotter and stays hot longer.
And spectrally, it often shows broad, smeared emission lines of hydrogen and helium, which is literally the shredded atmosphere of the dead star moving at relativistic speeds around the black hole.
Okay, so the AI is looking at millions of flashes, and it's analyzing the temperature, the cooling rate, the ultraviolet spikes, and the chemical fingerprints, all in fractions of a second.
Yes, it's doing all of that simultaneously. But this also brings up why we need AI to do this in the first place, rather than just having astronomers look at the light curves themselves.
Why couldn't a team of grad students just look at the graphs?
Because it touches on the fundamental reality of modern science. We are deeply entrenched in the big data era of astronomy.
Big data is almost an understatement here, isn't it?
It is a massive understatement. Modern survey telescopes don't operate like the telescopes of the past, where you pointed at one specific galaxy, took a long exposure, and developed a glass plate.
Like the old Mount Palomar photos.
Right. Today's survey telescopes continuously image vast swaths of the sky, night after night after night. They generate terabytes, sometimes petabytes, of raw data.
Petabytes.
They capture millions of transient events, things that flash, dim, or move every single night.
It's like trying to drink from a fire hose that is spraying the entire universe at you.
The volume of information has far surpassed the capacity of human eyes. Even if you had teams of thousands of humans to process it, it wouldn't be enough.
They'd just fall behind instantly.
If a human tried to look at every single flash recorded by a modern telescope to determine if it was a TDE, a supernova, a variable star, an asteroid, or just a reflection off a satellite, they would never finish a single night's data.
So the AI isn't just a convenient helper anymore.
Not at all. It is the fundamental, necessary lens through which we must filter the noise of the universe.
The AI is doing the sifting. It's panning for gold in a river of raw data, looking for a flake of gold that we used to literally throw away because we didn't think gold belonged in that part of the river.
It finds the impossible by tirelessly applying complex pattern recognition to datasets far too large for human comprehension. AI tools like Discore are becoming the primary engines of discovery in chasing down these incredibly rare astronomical events.
It's amazing.
They remove the human computational bottleneck and, critically, they remove the human bias.
So the AI looks at millions of data points It sees this specific super hot UV-heavy light signature 30,000 light-years off-center in the WISA galaxy, and it basically raises a digital hand and says, look at this. But finding a candidate in a computer model is one thing, right? Proving it is real, proving that a million-mass monster actually just shredded a star in the outer rim of a galaxy, that requires pointing physical glass at the sky.
Absolutely. A flag in a database is just a hypothesis. It requires rigorous observational confirmation. You need to gather the actual photons hitting the Earth.
You need proof.
This leads us to the critical ground game involved in this discovery. Once the AI flagged TDE 2025 ABCR, the Carolina team needed rapid, high-quality optical observation to confirm its nature before the flare faded back into the dark.
Because it's not going to glow forever.
No, it fades relatively quickly. And to do that follow-up, they used the SOR telescope.
The SOR telescope.
Yes, the Southern Astrophysical Research Telescope. It is located on Cerro Pachón, which is a mountain in the Chilean Andes.
Chile is famous for its observatories, right?
It boasts some of the clearest, driest skies on Earth. Perfect for astronomy. SOAR is a 4.1-meter optical and near-infrared telescope, and it is highly relevant that UNC helped build SR and continues to operate it as part of an international consortium.
Having your own 4.1-meter telescope on speed dial seems incredibly handy when you're hunting transient flashes in the dark.
It is the difference between capturing an event and missing it entirely. Benjamin C. Kaiser, a postdoctoral researcher at UNC Chapel Hill, pointed out the immense value of this facility.
Because of the speed.
When dealing with short-lived astronomical phenomena like a TDE, time is of the essence. The accretion disk will eventually be consumed or it will cool down. The evidence will literally disappear.
It's a ticking clock.
SOR allowed the team to rapidly follow up on the AI's candidate, point a highly sensitive spectrograph at those exact coordinates, and analyze the light to confirm definitively that this was indeed a massive black hole shredding a star.
But this wasn't just checking a box to confirm one event, was it? This specific optical confirmation is a monumental proof of concept for the entire field of astronomy.
It truly is a milestone. Researchers have stated that TDE 2025 ABCR provides the very first strong evidence that astronomers can reliably hunt for wandering supermassive black holes using ground-based visible light telescopes.
Let's make sure we underline why that is so important. Up until now, to find really weird, extreme stuff like black holes, we often had to rely on space telescopes looking at X-rays or gamma rays, right?
Usually, yes, like the Chandra X-ray Observatory.
And those space observatories are incredibly expensive, they have limited lifespans, and securing observation time on them is highly, highly competitive.
You basically have to win a lottery to get time on them.
But this proves we can find these invisible monsters just by looking for the visible flash of their meals from right here on Earth, using glass on a mountain in Chile.
It effectively opens an entirely new subfield of astrophysics. It proves the methodology is sound. You combine unbiased AI scanning of large optical survey data with rapid follow-up from agile ground-based optical telescopes like SR.
It's a 1-2 punch.
This combination is the blueprint for how we will map the hidden universe in the future.
And that future is coming fast. Because that fire hose of data we were talking about earlier, it's about to turn into a complete ocean.
We are standing on the precipice of an observational explosion. We have next-generation survey telescopes coming online very soon that will absolutely dwarf our current capabilities.
Give me some examples.
Well, the NSF DOE's Vera C. Rubin Observatory, which is currently being built in Chile, features a 3,200 megapixel camera.
3,200 megapixels, that's absurd.
It will essentially film a continuous high-definition time-lapse movie of the entire southern sky every few nights. It will generate 15 terabytes of data a night.
15 terabytes a night. Human eyes literally cannot look at that.
It is physically impossible. We also have the Roman Space Telescope, which will survey vast areas of space with incredible infrared resolution, and UNC's own Argus Array, which is a uniquely designed telescope system meant to monitor the entire visible sky simultaneously for rapid transient events.
So what does that transition look like for finding these things? If we've only found a little over 100 TDEs in the past decade, what happens when Rubin and Roman and Argus actually turn on?
The estimates are staggering. Astronomers expect to go from discovering tens of tidal disruption events per year in the relatively nearby universe to discovering many hundreds, if not thousands of them per year.
Thousands.
And at much greater cosmological distances.
Thousands of stars being shredded by black holes, spotted every single year.
Which means we won't just be finding the standard centrally located black hole anymore. By applying the unbiased AI tools we just discussed to this massive new influx of data, we are bound to find countless more wandering black holes.
Because we finally know how to look for them.
Exactly. We will finally be able to map their populations, understand their distribution across galactic halos, and finally piece together the full chaotic history of galactic evolution, of ancient mergers, and of three-body slingshots.
I want to connect this back to you listening right now. We've talked about billion-year-old galactic mergers, million-mass ghosts hiding in the dark, AI algorithms rewriting their own biases, and giant pieces of glass on mountaintops in Chile.
There's a lot of ground to cover.
It's an incredible narrative of scale, but why should you care? Beyond just the sci-fi cool factor of a rogue black hole eating a star, what is the actual relevance of this knowledge to humanity? Why does it matter to the physics of our own reality?
It matters because it is a question of fundamental physics. These extreme events, a supermassive black hole shredding a star, release enormous amounts of energy.
Energy we can't make here.
Exactly. They create environments with gravitational forces, magnetic fields, and extreme states of matter that are absolutely fundamentally impossible to recreate in any laboratory on Earth.
Right, like we can't build a black hole in a particle accelerator in Switzerland to see how space-time bends.
That would be ill-advised even if we could.
Very true. We can't compress matter into a singularity to see what happens to the laws of thermodynamics.
Precisely. We cannot generate those magnetic fields, those temperatures, or that extreme space-time curvature. Therefore, the universe itself must become our laboratory.
The ultimate testing ground.
Every time we observe a TDE, we are watching a fundamental physics experiment play out on a cosmic scale. By studying the light curves, the relativistic jets, the friction of the accretion disk, we are unraveling the bedrock laws that govern the entire universe.
The same laws of physics that govern the atoms in your body right now, sitting in your car or walking your dog.
Exactly. Gravity, electromagnetism, thermodynamics, these are the rules of the ecosystem we live inside. We are learning how gravity truly operates at its absolute extremes.
Testing the limits of Einstein's theories.
We are uncovering the full life cycles of stars and galaxies, the violent mechanisms of how structure forms in the universe. Every single observation brings us one step closer to understanding the mechanics of reality itself. We are not separate from these events. We are a byproduct of a universe dynamic enough to create them.
It is awe-inspiring to think about. To recap the sheer scale of what we've just covered, we started with a single star, drifting through a quiet galactic suburb, completely unaware that it was approaching a hazard it couldn't possibly see.
A cosmic ghost.
We witnessed it splintering in the dark, pulled apart by tidal forces, illuminating a rogue 1 million solar mass black hole that had been violently exiled from its home millions or billions of years ago.
And we saw how our own human assumptions almost hid it forever.
Right. Our belief that monsters only hide in the center of the room almost kept this ghost hidden, until we allowed an artificial intelligence to look at the data without our bias. We saw a telescope in Chile pivot just in time to catch the fading light, proving that we can hunt these invisible anomalies from the ground.
And we looked ahead to a very near future.
A future where new, massive observatories will soon find thousands of these violent cosmic meals, turning the night sky into the ultimate physics laboratory.
It is a profound reminder that there is always more to learn and that our understanding of the universe is constantly evolving. The cosmos is far more dynamic, chaotic, and beautifully violent than we often assume. But, there is one final piece of this puzzle, a final implication that I think we need to leave hanging in the air.
Oh, what's that?
Think about the math for a second.
Okay.
If a single massive galaxy can hide a 1 million solar mass black hole roaming its outer edges, an entity completely invisible, entirely undetectable, drifting silently through the suburbs until the exact moment a random star bumps into it.
Oh man, I see where this is going.
How many other silent gravitational giants are wandering through the dark right now? Perhaps even in our own galactic neighborhood, reshaping the universe in ways we cannot even see, just waiting in the pitch black.